we're going to find the tangent plane and the normal line to the following surface. It is z equals x plus y squared plus 1 at 1, negative 3. No, at 1, negative 1, 3. I'm asking you to pause the video and work it out. Okay, so you've done that. Let's look at it. Now, we need to rewrite this as z, well, in this case it will be negative z. If we subtract z from both sides, plus x plus y squared plus 1 is equal to 0. Now, remember, we will need to find the gradient. Remember, when you're dealing with tangent to a curve, looking at the gradient of the curve at that point. In this case now, you're dealing with tangent of a plane to a surface. So again, you're dealing with gradient, so you're going to have to differentiate. Now the gradient, well, remember, what we say here is that f, a vector f, right? Well, not a vector. F is equal to negative z plus x plus y squared plus 1 equals 0, alright? We're going to call this f. Now the gradient of f, well, is a gradient of a vector f is equal to the partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z. So that is a vector. Alright? Right. What we are also going to have to know is that the normal line, let's call it n, the normal line is going to be, well, the normal line equation. That's the equation to the normal line is going to be x is equal to x0 plus the gradient delta f by delta x multiplied by the parameter t. But I want you to think of it this way instead. Just like how you have y equal mx plus c, so the dependent variable is equal to the gradient m times the independent variable x plus a constant c. Here x is equal to the gradient, the partial derivative of f with respect to x, times t, I mean, not x, t, plus x0, the constant, the specific point, x0. Y is equal to delta f by delta y, the partial derivative of f with respect to y, which is a gradient function, times t plus y0, and z is equal to the partial derivative of f with respect to z times t plus z0. So it's kind of look like y is equal to mx plus c. As remember, m is the gradient and the derivative is the gradient function, alright? Alright, so here now, That's going to be the equation of the normal line. Remember, our x0 is equal to 1 based on what we have here. Y0 is equal to -1. Z0 is equal to 3. Alright? As for the equation of that plane, it's going to be the partial derivative of f with respect to x times the change in x minus x0 plus the partial derivative of x with respect to y times y minus y0 plus the partial derivative of f with respect to z times z minus z0 equals 0. Alright? Now, remembering the normal line to the equation, you could remember your y column x plus c, and then you remember that it is the independent variable is equal to m, which is your gradient. When you differentiate, you have a gradient function times the independent variable plus the y-intercept in the case of straight line, as we did before, but here is y0, and the x and the z are written in the same way. Alright? You can remember that the gradient of the function, the gradient here is a vector. Here you have delta f by delta z and so on. Those are gradient functions, derivatives. And this will be at the point 1, -3, no, I say -3 again, 1, -1, 3. Alright? Now, also, if you manage to remember the equation of the tangent plane, this is the equation of the tangent plane, equation of the tangent plane. If not, you could try and reason it out, and this might enable you to remember it even more. You have a plane, it's tangent to some surface, alright? And it might touch the surface somewhere here. If you have this plane and you have various vectors to it, right, you would see that there's an infinitely large number of vectors. Now, suppose you take a vector that is orthogonal to this plane. In other words, it's 90 degrees to any other vector on this plane. Then the dot product between this vector and the vectors on the plane must be 0 because they're 90 degrees apart. Now, if you have a specific point which you call x0, y0, z0, which in this case is our specific point here, 1, -1, 3, and you consider any point at all, any general point, x, y, z, it could be anywhere. A vector joining x, y, z to x0, y0, z0 will be x minus x0, y minus y0, z minus z0. Now remember, it would be good to, if you're going to get an exam and not given formula sheet with this, it's good to remember it. Alright? But looking at this might help you to remember the formula. Alright. Now, here it's like you're saying you have the three axes. You have x, y, and z. X to my right, y to my left, z going straight up. Now, if you look at any point here and say a location to x0, y0, z0 could be x minus x0. So here, x minus x0, your x could be here. Then y minus y0 would be the length of this other vector. And then you go straight up, z minus z0. So you move x minus x0 in the x direction, y minus y0 in the y direction, z minus z0 in the z direction, right? So in this case here, if this is your x0, y0, z0, and this is your point, any point, or whatever point it is, right? X, y, and z can be any point. This vector, joining them, going straight up here, the x, y, and z components would be x this distance, which is x minus x0, y this distance, which is y minus y0, z this distance, which is z minus z0. And if the normal vector has components a, b, c, the dot product between these would be 0. Now remember, this is a vector. I didn't write the vector notation here. This is a vector. So in this case, the dot product would be x minus x0, y minus y0, z minus z0. It would be like saying x minus x0 times I, y minus y0 times j, z minus z0 times k. You remember your vector, where I, j, and k would be the direction, x, y, and z, alright? Dot, and then you have a, b, c. So, in this case now, the dot product would be a times x minus x0 plus b times y minus y0 plus c times z minus z0. Alright? That's the dot product. And the dot product is equal to 0. Now, a, b, and c, in our case, would be the partial derivative. A would be partial derivative of the function with respect to x, b would be the partial derivative of the function with respect to y, c would be the partial derivative of the function with respect to z, which we have up here. Alright? So we have the formulas. Now, let's work them out. We want to find the gradient. We have f is equal to negative z plus x plus y squared plus 1 equals 0. So the function is negative z plus, what was it? X squared plus y equals 0. Was that it? Negative z plus x plus y squared. Okay, it's really x plus y squared. It was x plus y squared. Oh, was there a plus 1? Yeah, plus 1 equals 0. Alright, so in this case, we say plus 1 equals 0. Alright, so the gradient here, the gradient of the function would be delta z by delta x, in this case 1. Remember, z is a constant, y is a constant for now. Alright, then you have what you have here is going to be, well, we have x here. Alright, was it x squared? Let me see something. What was it? Okay, so here is x. When you differentiate x with respect to x, you get 1, and then 2y. Alright, so there we have the gradient of that function. Alright, now what we're going to do is substitute these at the point. What were the points again? 1, negative 1, 3. Alright, at 1, negative 1, 3, the gradient is equal to, this is remains 1, this remains 1, y is negative 1, so 2 times negative 1, negative 2. Alright, now here we know our partial derivatives at the point 1, negative 1, 3. We want the normal line, so we substitute it in the equation of the normal line. Remember, x is the gradient times t plus x0. So x is equal to delta f by delta x t plus x0. In this case, delta f by delta x at the point, we know it is 1 times t plus x0 is 1, so it is t plus 1. Y is equal to delta f by delta y t plus y 0, which is delta f by delta y. In this case, at the point that we're looking at, it is 1 times t plus, and then y0 is negative 1, so it is t minus 1, and then z is equal to delta f by delta z t plus z0, which in this case, delta f by delta z at the point, it was negative 2t plus, and then our z0 is 3, so it's plus 3. Alright, so those are parametric equations to the function. We could very well transpose for t and say t, in this case, no, we could yeah, right, we could transpose for t and say x is equal to, alright, let's rewrite this before we transpose so we can see it more clearly. X equal t plus 1, so when we transpose for t, t is equal to x minus 1. You see that? Y is equal to t minus 1. So when we transpose for t, t is equal to y plus 1. And here, z is equal to negative 2t plus 3. So t is equal to z minus 3 over negative 2. So what we could do is equate all the t's. t is equal to t. So you say x minus 1 is equal to y plus 1 is equal to z minus 3 over negative 2. Alright? So here we have our equation of our normal line. What about the equation of the tangent plane? Alright, we have the formula for it. The derivative times the change of each x, y, and z, and all of that equals 0. So let's see how it goes. Remember, what we have is the derivative of f with respect to x times x minus x0 plus the derivative of f with respect to y times y minus y0 plus the derivative of z with respect to z. What am I saying? The derivative of f with respect to z times z minus z0 equals 0. And this would remind you of the formula where we have delta z is equal to, del z is the small change in z is delta z by delta x times a small change in x plus delta z by delta y times a small change in y. Remember that? That change in x would be x minus x0. We have our delta f by delta x. Alright? So remember that formula. But anyway, let's continue with this as it is. Now, our delta f by delta x. Remember, each of these occur at the point. So we're going to substitute each of these at the point. What was the point again? 1, negative 1, 3 at 1, negative 1, 3. All of these occur at that point. Alright? Now delta f by delta x. What was it again? Delta f by delta x at here is 1 and then 1 and then 2y. Well, when we substituted 2y, what did we get? 1, 1, negative 2, right? 1, 1, negative 2. So delta f by delta x is 1, x minus x0. Let's write it as x0 for now, plus delta f by delta y at the point is 1, y minus y0, plus delta f by delta z at the point is, what was it again? Negative 2 plus negative 2 times z minus z0 equals 0. Now remember, based on what we have here, this is x0, this is y0, this is z0. So x0 is equal to 1, y0 is equal to negative 1, z0 is equal to 3. So we substitute them and see we have x minus 1 plus y minus negative 1, which is y plus 1, minus 2 times, and we have z minus 3 equals 0. Could multiply out the brackets. We run out of scrolling space, so let's continue working on this side. We could multiply out the brackets. X minus 1 plus y plus 1. We have x minus 1 plus y plus 1 minus 2z plus 6 minus 2z plus 6 equals 0. So x plus y minus 2z, negative 1 plus 1, that's 0, plus 6 equals 0. And we could write it as x plus y minus 2z is equal to negative 6. So that's the equation of our tangent plane.